A 1.5-liter engine from the 1980s produced around 60 horsepower. Today, a 1.5-liter engine in a family hatchback produces 180. Same displacement, 3 times the power. The answer fits in a shoebox and runs on exhaust gas you were throwing away anyway. An internal combustion engine is an air pump with controlled explosions inside it. The more air you can push through it, the more fuel you can burn, and the more power you make. Engineers used to solve this by making engines bigger, more cylinders, larger bores, greater displacement. A 5-liter V8 moves a lot of air because it physically has more space to do so. But bigger engines are heavier, drink more fuel, and take up more room. The auto industry spent decades building ever larger engines to extract more performance, until fuel prices and emissions regulations forced a different approach. The question became, what if you could feed a small engine the airflow of a much bigger one? Every time a cylinder fires, it pushes the burned gases out through the exhaust. Those gases are hot, around 800 degrees Celsius, and they leave the engine at high velocity. For decades, that energy was simply thrown away. A turbocharger captures it. The device has 2 wheels connected by a single shaft. One wheel, the turbine, sits in the exhaust stream. Hot gas spins it at speeds up to 200,000 rotations per minute. The other wheel, the compressor, is on the other end of the same shaft. As the turbine spins from exhaust energy, the compressor spins too, and it forces compressed air into the intake manifold. More air enters the engine than the cylinders could pull in on their own. You are using waste energy to supercharge the intake. Atmospheric pressure at sea level is roughly 1 bar. A naturally aspirated engine draws air in at near atmospheric pressure because it has no assistance. A turbocharged engine can push air in at 1.5 to 2 bar or higher, meaning the 100% denser than ambient. A 1.5-liter engine breathing at 2 bar of boost is effectively moving as much air mass as a 3-liter naturally aspirated engine. The combustion is proportionally more powerful without adding a single millimeter of displacement. But there is a catch. Compressing air heats it, and hot air is less dense. An intercooler sits between the turbo and the intake to cool the compressed charge back down before it enters the engine, recovering the density benefit the compression added. Turbochargers have one well-known limitation: lag. The turbine only spins fast enough to build boost if there is enough exhaust energy, which means enough engine load, which means you have to be driving hard enough already. At low engine speeds or light throttle, boost pressure is minimal, and the engine behaves like a naturally aspirated unit. Press the accelerator firmly and there is a brief delay, sometimes half a second to a full second, before the turbo spools up and boost arrives. Early turbocharged cars from the 1970s and 80s made this painfully obvious, with a sudden surge of power arriving late and unpredictably. Drivers called it the turbo kick. It made the cars exciting and occasionally terrifying. Engineers have spent 40 years reducing turbo lag. Smaller turbines spool faster because they have less rotational inertia, but they also flow less air at high engine speeds. Twin-scroll turbines separate exhaust pulses from different cylinder banks to maintain a steadier energy supply to the wheel. Variable geometry turbines use adjustable vanes to tune airflow over the turbine wheel across the entire rev range, keeping the wheel spinning efficiently at low speeds. Twin-turbo setups pair a small turbo for low-speed response with a larger one for high-speed output. The result is a modern turbocharged engine that builds usable boost almost immediately from idle and holds it smoothly through the rev range, eliminating the character that made early turbos notorious. The shift from large, naturally aspirated engines to small turbocharged ones, a process called downsizing, accelerated rapidly after 2010. European emissions regulations punished high-displacement engines. Consumers expected both performance and fuel economy. Turbocharging delivered both. A modern 2-liter turbocharged 4-cylinder matches the A, 3-liter naturally aspirated 6-cylinder while burning significantly less fuel during light load cruising, because when the engine does not need peak power, it runs as a small displacement unit. The turbo only contributes when demanded. The result is that the average passenger car sold today produces far more power per liter of displacement than any comparable car from 20 years ago, while also meeting emissions standards that would have been unimaginable then. The turbocharger turned the exhaust pipe from a waste outlet into a power source, and that single insight is the reason most engines built today are half the size they would have been a generation ago.